The title of this note is Optimization, and the outcome is that I'll be able to set up equations in order to optimize a quantity. So optimize sounds like optimal. It's all about getting the best. So optimization is used in a lot of business and engineering. If you want to design, say, like a cereal box or a soup can, you want to figure out how you can get the most product out to your customers using the least amount of packaging as possible. So we need to optimize our shapes so we can do that. So here's our strategy. There's a lot of words here. See if you can sort of summarize this to put it in your notes. So first you're going to write what we're going to call a primary equation. It's the one that has the quantity that you're trying to optimize. Secondly, you have to check that your primary equation has only one independent and one dependent. So if you have more than just two variables, an input and an output, you're going to need a secondary equation, and you're going to use that to sort of transform your primary equation. I'm going to show you how to do this here shortly. Third, you're going to need a feasible domain. Fourth, you're going to find your maximum or minimum. This is what we've been practicing. Okay, so there's no summary below because you know how to find maximum and minimum. And then lastly, you need to make sure that you've actually answered the question. So let's look at an example here. All right, so we are going to enclose a rectangular field with a fence. We have 500 feet of fencing, and the building is on one side. So it's always helpful to draw a picture. So we have a building. And so we are enclosing the field on only 3 sides of the fence. And we know that we have 500 feet of fencing. And it is a rectangle. So maybe I have my length and my width. So I know that those two sides are the same. So it says determine the dimensions of the field that will enclose the largest area. So I'm marking my text there. That's telling me that I am trying to, largest means maximize. I'm looking for a maximum area. So my primary equation needs to be an area equation. So the area of this rectangular field, I know that the area of a rectangle is the length times the width. But notice I have 3 variables. I have an output variable, but I have 2 different inputs, and that's not okay. So I need a primary equation. So this is the primary. I need a secondary equation, the constraint. My constraint is that I only have 500 feet of fence, and it has to cover 1 length and 2 widths. I'm really just adding W plus L plus W, but I simplified it here. And that has to equal 500. So what I need to do is I need to change my primary equation so that it only has an L or a W, and it really doesn't matter here. So I'm going to solve this 500 equation, the secondary equation, for 1 variable. I'm just choosing L. It doesn't matter what choice you make here. So 500 minus 2W equals L. So what I can do is I can go back to that area equation, and instead of writing L, I'm going to write 500 minus 2W times W. That still says length times width. So that was all step 2. Let me go back to the steps here. So my primary equation was the area, because that's what I was trying to optimize. And then my constraint, or my secondary equation, was that I only have 500 feet. So now I'm going to write down the feasible domain for the area. And I'm thinking, well, obviously I can't have any negative numbers. And I'm wondering how large this can go. And I'm thinking the largest here, maybe if this was a square, it'd be pretty big. I've only got 3 sides. I'm just estimating domain here. It's all about picking numbers that make sense. So I'm thinking if I have 3 sides, if I have 500 feet, I wonder if that's 500 divided by 3. Well, that's really tough. So I'm just going to round. Instead of doing 500 divided by 3, I'm going to do 600 divided by 3 to get 200. So I'm just saying, well, probably the most this can be is a 200 by 200 square. And if I took the area of that, it would be 40,000. So I'm probably looking at numbers between 0 and 40,000 for my largest area. What's most important for me to recognize is that my answer has to be positive. So if I have any negative values, I know they're not making sense here. Okay, so now I'm ready to optimize this equation. So I'm looking for the largest area, or the maximum. So I'm ready to find a maximum. So I'm going to find the derivative. And I'm going to notice here, wow, I really don't want to do product rules. So I'm actually going to back up and distribute that W. Okay, good. Now I don't have to do product rule. Let's try that again. So A prime would be 500 minus 4W. And I'm looking for my critical points, so I'm going to set that equal to 0. It'll never be undefined because there's no division there. So W equals 500 divided by 4. And that's 125. That's my critical point. So now I'm thinking about my sign chart. I know the width has an endpoint at 0. I know 125 is a critical point, and my width has a maximum 500 because I only have 500 feet of fencing. Okay, so let's check our sign. So between 0 and 125, I'm checking the sign of my first derivative. So I'm plugging it into this thing right here. So I'm going to pick a really convenient value. How about 1? So 500 minus 1 is a positive value. And then I'm going to pick a number between 125 and 500. I want to try to be as simple as possible. So how about 200? So 5 minus 4 times 200, that's 500 minus 800 is negative. And so I'm thinking, well, 125, if my first derivative changes from positive to negative, that means I have a maximum. So my maximum occurs when the width is 125. So we've done step 4. We've found our maximum. Now we need to do step 5. We need to make sure we've actually answered the question. So we know the maximum occurs when the width is 125. The question, I'm going back to the text, determine the dimensions of the field that will enclose the largest area. So dimensions is length and width. I know that the width is 125. If I want to figure out the width, if I want to figure out the length, I'm going to use that secondary equation, knowing that the width is 125. That's 2 times 125 that I'm writing right there. So 2 times 125 is 250. So the length is 250. So now I've answered the question. The question is, what are the dimensions that will enclose the largest area? And the answer is a width of 125 and a length of 250. Let's look at one more example. Okay, so we want to construct a box whose base length is 3 times the base width. So it's always helpful to draw a model here. So we have a box, a 3-dimensional box there. And we know that the length is 3 times the width. The length is equal to 3W. The material to build the top and the bottom costs $10 per foot. And then to build the sides, it's $6 per foot. We know that it has to have a volume of 50 cubic feet. We want to determine the dimensions that will minimize, so I'm looking for a minimum, the cost to build the box. So my primary equation is an equation for cost. So the cost of this box is that the top and the bottom is $10 per square foot. So that's going to be $10 times, length times width would be the top, and then it's also $10 at the bottom. So if I wanted to combine that, it's a total of $20 for the length times width, because there's two tops, all right? And then for the sides, it would be the width times h, and that would give me the measure of one side, and it's $6 for one side. There's 4 sides, so I'm paying a total of $24. So that's my primary equation. Notice it has 3 variables, L, W, and H, okay? First, I know that L can be replaced with 3W. I'm going to go ahead and do that. So, but I still have an H in there, so I need my secondary equation. My secondary equation is going to be that the fact that the volume, which is length times width times height, is constrained at 50. I already know that L is 3W. And so 3W times W is 3W squared. It'd be a lot easier to solve this for H than for W, so that's what I'm going to do. So H equals 50 over 3W squared. So if I go back to my cost equation, cost is 20 times 3W squared plus 24 times, this will be now W times 50 over 3W squared. I just want to do some simplifying. And I'm going to simplify even further. 24 divided by 3 is 8. So I'm doing 8 times 50, which would be 400 over W. So I want to find the minimum. So I'm now ready to optimize this equation by finding its derivative. Before I do that, I really don't want to do quotient rule. So instead, I'm going to write this as 400 W to the negative 1. And now let's find the derivative. That's the same thing as 120W minus 400 all over W squared. So I'm optimizing this. I want to find my critical point. I should think about my domain. I skipped that part. Let's go back and look at the text just to think about the domain. We weren't really giving any constraints about the size of the box. It was more about the cost. But we do know that everything has to be positive. So my domain is going to be all positive numbers. So 0 to infinity is my domain. I have to have positive numbers here. It wouldn't make sense to have negative numbers. All right, so I want to minimize the cost. So I have that derivative. I want to find that critical point by setting it equal to 0, or it does not exist. And I can see right away it would not exist if W is 0, because then I'd have division by 0. But does this thing ever equal 0? I'm going to add 400 over W squared to both sides. And then I'm going to multiply both sides by W squared. So I now have 120 W cubed equals 400. I'm going to divide both sides by 120. Sorry, that's 400. I mix the 400 and the 120 together. I see right away they're both divisible by 10. Those are both even. Hey, those are both even. Okay, so it's 10 over 3. And then I'm going to take the cube root. So W equals the cube root of 10 over 3. I could get that as a decimal calculator, but it really doesn't matter. All right, thinking about my sign chart. I actually don't need this critical point 0 because it's not in the domain. Remember, your box cannot have a width of 0. Our domain was not including 0, so not in the domain. So the only critical point we have is the cube root of 10 over 3. So something that's less than that would be 1, because 1 is less than 10/3. So let's plug 1 into our derivative. So going back up here, 120 times 1 is 120, divided by, and then 400 divided by 1 is 400. So 120 minus 400 is a negative value. And now we're going to pick a value that's much bigger than the cube root of 10 over 3. So 10 over 3 is like 9 1/3. So if I pick the cube root of a number that's bigger than 9, I'll be fine. I know the cube root of 27 is 3, and 27 is definitely more than 10/3. So I'm going to pick 3. So plugging 3 in, 120 times 3, I do need to jot this one down, is 360, and then minus 400 over 9. I'm going to go to my calculator here. I'm getting a positive value. So I can tell that's my only critical point. I can tell that that's going to be a minimum. So then again, going to my question, I got to make sure I answer the question. It says, determine the dimensions that will minimize the cost. So we know our critical point is at the cube root of 10/3, and that variable was w. So the only thing we've solved right now is the w is the cube root of 10/3. We know that the length is 3 times that. And then to get the height, we would have to use our volume formula. So we know that volume is length times width times height. So I just moved some stuff so I had some room. So length times width times height. And I know the volume is constrained at 50. And I know so 50 equals 3 times the cube root of 10/3 times the cube root of 10/3 times h. There's 4 of those. So then h is, and I don't need to simplify, 50 over 4 times the cube root of 10/3. So there's the answer to my question. Those are the dimensions of the box that is the cheapest. That is going to be the end of these notes.